Great, so let's get started, everyone. So the last lecture before spring break. We'll, so so we'll keep talking today about joint random variables. We'll finish up discrete random variables through looking at the independence of them, and then I'll get started on the continuous random variables as well. If you look at the schedule, kind of the continuous random variables are split between now and after break. That's probably good because it's going to be like a week and a half before the next lecture. So I'll get to review them a little bit. I'm thinking, and we'll see how it goes, that the next 4 lectures, I might actually only need 3 lectures for. So we'll see if that works. If that happens, I'll get to do an extra topic and statistics later in the semester. If we don't finish everything, that's fine too. So that if it takes like what's on the schedule, but I might kind of get to statistics, the intro to statistics on the Tuesday after break. So we'll see. Your quiz number 7 is. So today, again, this won't open until 5 p.m. now, and I'll do a little review of the last 15 minutes or so of class. Hopefully this kind of, helps you figure out what to focus on. Okay, and you can ask questions if you're concerned, and instead of it being kind of right at the end of the material, so right into the quiz, hopefully this ends up working out a bit better. So we'll see. Okay, and homework 4 is out. It's due the Tuesday after break. Hopefully you've got started on that. Not, you can do it over break, or a lot of people do it the last couple days before it's due. Hopefully you don't always wait till the last couple days, but so it should be on the stuff we've already covered even so a week ago. So hope you get started on that. We won't have office hours or help hours over break. Okay. And homework 3, I think, is almost done grading. A lot of the TAs have some midterms this week too, but it will, so hopefully the scores for that will be out soon. So, okay. Let's see. Okay, we're talking about joint random variables. And so let's just review a little bit. We're going to consider 2 random variables, x and y, right? So we had talked about joint probability before, and then random variables, but not joint random variables. How do 2 random variables interact with each other until the last lecture. And so we've been talking about this for discrete random variables so far. And we're going to do that and then get into continuous random variables and kind of redo a lot of the same stuff, but it's a little trickier because you have to do like integrals. So it's easier to see it with discrete random variables first. And so the key thing in representing these, so you have joint PDF, and we f instead of and we'll represent this as a function f, and it will be over 2 random variables. So then it is there are 2 different values that these random variables can take. X can take on a value A, and Y can take on a value B. And for a discrete case, this is equal to the probability X is equal to A and Y is equal to B. And so if you remember so this is a shorthand for so for these like events that the random variable takes on the value A, that's actually an event from the sample space, the subset of the possible outcomes. And same with y equals b. And this is shorthand for the intersection of those two things, right? Okay, so remember, this is shorthand for the set x is equal to A, intersection y is equal to b. So these have to occur at the same time. All right, and we had, and so if you have the PDF, then you can derive a lot of properties of this. And we had kind of considered this example, which I'll probably come back to today, where we had these, there's like a channel, and there's some noise on the channel, and the input is either a 0 or is a 1, and this is the sender, and the output is either a 0 or a 1. Okay, and this is the receiver. Okay, and so there should be some correlated. If the sender sends a 1 bit, then hopefully you're more likely to see a 1 bit on the other side of the channel, but it might get flipped, right? And so the example we had, just to recreate this so it's consistent in your notes, is you can write this as this table. Where the sender can be a 0 or a 1, receiver can be 0 or 1, and this was 0.45. Is this the same thing I had before? Did I swap flops 0 and 1? The same, okay. If it was sent a 1 bit, it may have also received a 0 bit. So that would be this event that happens 6% of the time. 8% of the time, the sender sent a 0 bit and the receiver got a bit that was 1. And then the remainder, 0.41, it's the probability that S sent a 1 bit and the receiver also received a 1 bit, right? And I say this is the remainder because these values these are different disjoint events, so they have to add up to 1. There are no other options other than a 0 bit or a 1 bit here. So these are the only options, right? Yeah. Yeah, so these are the S in this case are these random variables. The R is the receiver, and S is the sender. Okay, so there's some channel. This could be like a wire you send stuff across. It could be like the Pony Express, you know. You're sending a pony to send either a 0 or a 1 bit, you know. That's why they invented telegraphs, because that was not very efficient. But so you know, and there's noise in the process, right? So you would like these to be kind of, you know, what you would like is that these values are close to 0, and that you might not have an even distribution of 0 bits and 1 bits, right? But we can figure out the probability that the sender, right? So this table represents f of SR, right? So I can say 0, 1, that's the probability. This value corresponds, this 0, 1 corresponds with the sender 0 and the receiver 1, and the value is 0.08, right? 0.08, right? We would like those values where the bits flip to be so close to 0. Okay, and you can also derive the probability that of just the distribution of what the bits that were sent. So f of s of 0, this is equal to the probability that S is equal to 0, that the sender used a 0 bit, well, that's the sum of that row in the table, right? So 0.53 and f of S equals 1, probability S equals 1 equals, that should be 0.47, right? Yeah. Well, okay, so this is a simple example. At the prep for the quiz, I'll review with the kind of a more with a larger example. But the random variable can take on. So this looks a lot like the event R was true and the S was true or not. But I should think of these as values. These it could take on more than 0 or 1. It could take on a value, say 1 through 10. Right. So let's say S sent a number between 0 and 9. Okay, then I can have a larger table here. And those are the values that S can take on. I can think about the expectation or the variance of those values. And that's something we will, yeah, so the expectation is kind of straightforward. You do the expectation of each of the events individually. But we'll talk about how you think of the variance with joint random variables, and that's called the covariance. And we'll talk about that so like after spring break. Okay, so when you think about the variance, they could vary together or against each other, of course, and this will relate to things like correlation, which measures how similar are the distributions to each other. And these are things you can do with joint random variables that you don't do with just events. Okay, so I have a richer information, and we'll see later in this lecture, you can do this again with continuous random variables, right? And they can think of, instead of having just a binary distribution over binary values, you could have continuous values on these on the x and kind of the y-axis, and how do those overlap? Okay, so we're kind of building up towards that. So correct. Yeah. Yeah, there could be, if there are more possible outcomes, you could have more complicated joint events. Like if this value 0 through 9, you could say the event is all the odd numbers, right? That would also be an event. But you could also think of the expected value, because these are real values and I can take an average of them, right? Or a weighted average using the probabilities. So, okay, great. So I hope this is pretty straightforward. One thing, so let me say something new that we have not done yet. You can, I want to ask you one thing. What are these? We had a name for these distributions I wrote in blue. The marginal, no, I just said that I was going to ask you what that was. Okay. The blue distribution is the PDF of the random variable S. It's going to ask you what, I was going to ask you, what is that called? Okay, it should be easy. I accidentally blurted it out. Yeah, that's the marginal distribution. Good. Okay. Hopefully that made it easier to remember. Been known to blurt stuff out sometimes, so apologies. So okay, right. So this is the marginal distribution. All right. So you can right in the margin, you marginalize out the variable R. I've gotten rid of the variable R to get the marginal distribution over S. Okay. Okay. Something new that we haven't quite seen yet, it shouldn't be too much new, but is the notion of independence of random variables. Okay. If I have, before we do this, Okay, let's first do independence of events A and so B. Well, so if I have two events which are independent, what properties do they hold? Remember, is independence of events. Yeah. Well, that's kind of the right pieces there, but not quite the right thing. So this is equal to, if they're independent, it implies that that's equal to the probability of A. Okay? So the probability of A, so given B is same as the probability of A, right? The fact that I know the event B is true does not change the probability A is true, right? Yeah. Or is this probability A intersection B? Yes, the probability of A intersection B is equal to the probability of A times B. Yes, that's another formula of so the implications of A and B being independent events. There's a third one. These are all equivalent to each other. Yep. Yeah, so that's right. The probability of B given A is equal to the probability of, so B. Okay, if I have one of these events is true, then all of them are true, and I have independence between these events. These three statements are equivalent to each other, right? There are four statements, three equations. The three equations and the statement independence of events A and B, these are all equivalent to each other. Okay, I want to talk about independence now of random variables, X and Y. Okay, so I have random variables X and Y that are independent. Okay, so now if my random variables are independent, this is not quite the same thing. So I have a stronger statement. This is a stronger statement. The random variables are kind of defined based on the ingredients I have here are f of x, f of y. These are the PDF of x, the PDF of y, and the joint PDF x and y. Okay? So I can have whole probability distributions, and I can write them either, those are like the marginals, f of x, f and y, and the table, f of xy, right? When I have the joint distribution of them. What properties should I have for the independence of these? What do you think? Yeah. Yeah, so probably what you're saying is you probably, I can look at like any of these properties. Let's look at this one, right? Okay, so I probably want f of x, y, a, b, right? So that there's a particular value that x can take on a and y can take on b, right? That defines a particular event, right? Okay, and I probably want some property that looks like f of x a times f of y b. I probably have this property, right? That the joint probability of f of xy AB, so that means X takes A and Y takes B, that's equal to the probability that X takes A and the probability Y takes B, right? This statement, remember, is equivalent to the probability of X equals A and Y equals B is equal to the probability of X equals A times the probability of Y equals B, right? So that seems that's pretty close. These actually define, remember, so these guys define events, and I could say actually that this event was called A and this event was called B, right? And so this was actually A intersection B, and then that's equivalent to this statement. Okay, so if I have independence, this seems like the right thing to be looking for, but this statement. So this statement is for a particular A. I want the claim that the random variables are independent does not, I just talk about the random variables and I have these PDFs, but the statement I've written here, right, this depends on this A and this B, these particular values that it takes, right? So that wasn't in my claim about the random variables, which lowercase a, which lowercase b. Yes, for discrete random variables, we can directly map the PDF to the probability. Yeah, we'll have to use integrals for continuous, and we'll do that in like 10 minutes. We'll do this all over again with integrals. Yeah, but I can directly map it to the all the math. I like using the F notation for both the discrete and continuous because the math basically works out the same. The sums just turn to integrals. Okay, but it's a little bit more confusing when we do integrals. So we're doing this first, right? Okay, so I asked the question. So for which values of A and B should independence say something about? All right. Well, okay. So the answer is this holds for all values A, B. Okay. So when I have independence for random variables, I get this independence of the events for all possible events, not just one possible event, but it has to hold for every single possible event. Okay. So if you want to check this, if you have a table, if I've given you a joint probability table, right, you're going to think of having a table. It's going to have a bunch of these cells, right? And I'm going to have, say this is X, Y. This is the marginal distribution. F of Y is here. The marginal distribution for F of X is here. And then for any entry, right, so this would be kind of some values A and B. I have to check F of X A, F of Y of B, and this one is F of X, Y, A, B, and I have to check, does F of X, Y, A, B equal to F of X A times F of Y B, right? So I need to check that this is true, right? This is the probability that the events X takes on A, Y takes on B are independent of each other. But for the random variables to be independent, this needs to hold for all possible events, right? So I need to do this comparison for all possible events. to check that this independence holds. Yeah. So yes, that's a good point. Yes. Right. So what do we typically do in practice? If they're not independent, you kind of look for intelligently where do they look like they're not independent and check that. And you only need one example for them not to be independent, for this equation not to hold, for the whole random variables not to be independent. Okay, so to find they're not independent, you just need to find one instance where it violates it. For them all to be independent, you need to kind of verify it for everything. In practice, what we typically do is we actually do this in reverse, in that we tell you that they're independent, or we model something as independent, or we kind of control a process so they're independent. Like I flipped a coin, and then I flipped the same coin again. Okay, but I didn't look at the outcome of the heads of the coin the first time when I flipped the second coin. They should be independent of each other. I rolled a die, so rolled the same die again, right? So those should be independent. And then what I can do is I typically I can then use this equation. I can say, well, I don't want to fill up the whole table, but I can write down the marginal probabilities, and I can implicitly store the table as the product of them, right? So if I want to store like there are n different values, I don't want to store n squared values. I want to store 2n values, and if I need the product, I just multiply them, right? So that's typically how the independence is used, that it's given to us, and then that allows us to either store it compactly or to do some cool kind of math derivations with it, which you'll see if you take machine learning. So, okay. Okay, so that's how we're doing. So I want to okay. The other thing this implies, independence, independence of random variables x, y, implies that any two events, so I can define event A, which is x, which is the union over x takes on AI for A in some set uppercase I, and so event B, which is a union over all J in Y BJ, that these events are also independent. Okay, so what does that mean in this picture here? If I had two events, let's say in the Y, it's column 1 and column 4, and in X, so this would be event B, and so then in the Y coordinates be column 2, column 5, and column 6. This would be event A. This would be A2, A5, and A6, right? So this would be corresponding with A, that any two of these events are also going to be independent. Okay, so I don't have to look at just individual values, but I can look at sets of values that I can take as well. Okay, so that implies, so this implies that the events A A and B are independent. Okay, so that I can look at any events defined over like over the outcomes of the random variables are also still going to be independent. All right, and I can write this. Here, let me just kind of work through this calculation's hopefully a little bit so useful to see. If X, that means X is in this event A, that's the event A is X takes on one of the values A, and also that I have Y takes on a value in so the set B, right? So now I can kind of expand this out using some rules I know, and I can derive, so I should be able to derive the probability of X in the event A times the probability of Y, so in the event B. This will kind of be useful to see because when we're going to talk about continuous random variables, we don't measure particular values. We measure kind of integrals of values. So we can do it in a discrete sense with sets here, with sums, and then the same argument's going to work with integrals with continuous random variables, but I'm not going to go through that argument. Yeah. Yeah, so these define, let me get the colors right. These define the sets of indices of values that the random variable can take. And this defines this set here, right? So there's a subset of values that the random variable can take. Let's say that the Y here, this kind of board example, the Y can take on, I flip two coins and I get a binary random variable between, 0, 0, 0, 1, 1, 0, 1, 1, or 0 through 3. And A is I'm like rolling a die, okay, and I get 6 values, right? And so the event A is I roll the 2, 5, or a 6, and event B is that I got all heads or all tails. Okay, but I can describe that by describing some indices. For the event, the set I, which is over A here, it allowed me to take on values 2, 5, or 6, and the event on B, let me take on values B0 or B3. That one started at 0. Okay. Correct. That's what I'm going to show. I'm going to show if the random variables X and Y are independent, which means I can take this product along any row or column, then the events are also going to be independent. Okay, and there's kind of a proof by picture you can kind of imagine here. I'm adding up some stuff and I can do it by decomposing it, but I'm just going to walk through the algebra for like the next 1 minute. Okay. All right, so I can start here, and hopefully this kind of explains this a little bit as I walk through the algebra, but I can use the law of total probability on A. I can look at I in the set I, and I can write the probability as X equals AI in the set I times the probability that Y is the same thing here, that Y is in this, so the set B, right? And then I can also expand I in the set I, the sum J in the set J, probability X equals AI, Y equals B, so J, right? I can take the probability of A and B in that set is going to be the sum of all the products, right? So in this picture, it's going to be let's see, the place where these, so it's going to be this row intersect the rows where A is active and the columns where B is active. So these 6 cells are the things I'm going to be. I've written this. I've written this as a sum over those 6 cells. And I'm saying the probability of the events X is in A and Y is in B has to be in one of those. So like 6 cells, okay? And now I can use the independence of the events, right, to say that this is equal to I is in this again, the sum I is in the set I, J is in the set J times the probability X is equal to AI times the probability that Y is equal to BJ. Because I had independence, I assumed independence on the random variables, I can do this for every term in the sum. Okay. Then I can combine these back together again. Actually, the first thing I can do, I can split the sum. I can X equals I and I can factor out, I'm going to factor this guy out. It does not depend on J. This is probability that X is equal to AI. I've factored that out because it does not depend on J. Probability that Y is equal to, so BJ. And then these 2 terms, like this term is just equal to the probability of X is in A. And then this term is just equal to the probability that Y is in B. And that means I've gone now from here, from starting here towards the end, and this is what it means to be independent of the events, right? So the events A and B are independent because it satisfies this property. The joint probability is equal to the product of the individual probabilities. Okay, so if I know every single value has independence, I get every single event made up of those values is also going to be independent. All right, good. Okay, I'm going to ask you all to now do one example. Let's go back to my send bit and receive bit example. 0.0, this is 0, 1, 0, 1, 0.45. What was this? 0.08, 0.06, and 0.41. Are these random variables going to be independent? Yeah. No, I should be able to calculate this. Here, let me help by calculating f of S0. Let me write this back up again, 0.53, and f of S1 equals 0.47. These are the marginal probabilities. F of R0, this should be 0.51, and f of R1 equals 0.49. Okay, so there should be a way to determine if these random variables are independent. Okay? Yeah, right. So if you just look at, you said look at this value and this value, and I should multiply these, right? I should say f of RS 1 should equal to 0.47 times 0.49, right? Okay, if they're independent, this should hold for all for all kind of ways I take the product of the marginal probabilities to get the joint probability. Is 0.47 times 0.49. Let me try writing this one more time. Times 0.49. Is that equal to 0.41? Well, it's less than 0.25, right? 0.5 times 0.5 is 0.25. That's way too big, right? So these are not independent. So not independent. Okay, if you have a channel and you're sending bits across the channel and it's independent of what you receive and what you send, is that good? What? So no? Yeah, so why is that not good? Yeah, because, well, you might know what you're sending, but the receiver does not know what was being sent, right? The receiver gets no information across the channel if they're independent, right? The probability, if they saw one bit, that means that the probability of getting a 0 bit is independent of whether you received a 0 bit or whether you received a 1 bit, right? And that means it's not a very useful channel. If you can send information across channel, means they're not independent. That means you can communicate. You may be noisy, but you can repeatedly send stuff until you're more confident. That if I were to send 2 1 bits across the channel, I say, right, so if I were to say, what's the probability that the send was 1 if the received equals 1, right? So this is the conditional probability, right? You know, I can write this down. Remember, probability of S intersect, or right, S equals 1 intersect R equals 1, divided by the probability that R is equal to 1, right? Right, and this was, let's see, probably R is equal to 1, 0.49. This is equal to 0.41 divided by 0.49, right? So this is about 82 or something. Okay, so 82% probability if I received a 1 bit, I was sent a 1 bit. Okay, if let's say this was the first time I did this, right? There are rounds, and I went and I computed this again. The probability I sent equals a 1 bit, given that I received a 1 bit, and this was the second time I did it. I repeated the experiment. Okay, I would calculate this value again, and I would say that's probably independent of the last time, right? It's probably 0.82, and these are now independent. So let's say I'm going to send a 1 bit, but I'm not kind of confident you're going to get it, so I'm going to send it twice. What's the probability that I promise I sent the same thing, right? 2 times in a row. That's like the protocol, right? So what is the probability that the send that I say, if I tell you S1 equals S2, what's the probability that send is equal to 1 if R equals to 1 and R1 is equal to 1 and R2 is equal to 1? Okay, so I received 1 bit twice, and I promised I sent the same bit both times. Yeah, the same joint probability table, but I'm now using independence here. I'm using independence of the 2 trials, not of the table. The table's not independent. That means I communicated something. Yeah, this is a little bit tricky. So it's easier to compute the probability. It's so it's a 0-bit. Yeah, so it yeah. I'll just this is a little bit beyond what we've done. This is 1 minus the probability it was a 0-bit, and that was 0.18 squared, because those are so independent. So I would have had to guess wrong twice. And if I guess wrong twice, the probability that is smaller. So what's 0.18 squared? That's about, this is roughly 1 minus 0.0, let's say 35, right? So this is equals to 965, right? So if I do this repeated experiment, I boosted my probability from 82% to about 96%. Okay, and you can repeat this as long as you have some signal going across the channel that's not independent of what you sent, then you can send repeated bits, and you can say, well, I promise I'm going to send it the same thing twice, or maybe even 3 times in a row. And then you can check and you boost the probability of being correct. So this is kind of a common way. There are more complicated ways of coding information, but this is kind of a way of using the independence to be so positive here. Even though the table, the channel's not independent, it's encoding information, but repeated trials are typically independent. Yeah. Yeah, right. So if I had like a billion bits to send, I'd have to send each bit 7 times in a row with this encoding. I would maybe boost the probability to being kind of probably roughly 0.999, so 99.9% probability of each of the bits. I probably have some corruption. That's probably not the best way of doing it. So there are 2 answers to this. One, that's better than having kind of 18% of all your bits corrupted. So, okay. But there are better ways of encoding this than just sending the same thing. So, you know, just like repeated one time at, like just 7 times in a row. Okay. So there's notions of like information theory and stuff you can take in the ECE department must offer some information theory class, but there are more efficient ways how to encode this information to send it efficiently across a noisy channel. Usually your channels are not this noisy, but there usually is some corruption, and you can correct it if you kind of use the independence of, if you assume the corruption is going to be independent, then you can encode stuff and you can kind of still recover this. Like if you have really important information and you store it on like a cloud, you often have like a RAID system where you split the data across multiple disks and you store multiple copies of it. There are ways to kind of one way to reduce the space is to do like a compression on it and store copies of the compressed file. But 1 bit wrong in a compressed file and you kind of completely lose what's going on. If you send like a JPEG, which is an image, and you have 1 bit that's corrupted, it still looks like an image. And so it's not so bad. That's kind of okay if you lose a bit or 2 in an image, but if you have a compressed file and you have to decode it in a complicated way, 1 bit gone wrong is catastrophic. And so you have to think about trading off these issues. And there's a whole cool field of information theory, and this is the very first piece of it. So yeah, yeah. Okay, cool. All right. Oh, I want to say an example. Yeah, I want to give an example where there is independent. So events, but not independent. So random variables. So okay. So I'm going to have an example with so two dice, okay, and they are not going to be fair. So not well. There's two dice. One is fair. Let's say D1. It can roll a 1, 2, 3, 4, a 5, or a 6. Okay. And so the probability of rolling these, well, rolling a 1 is 1/6. Rolling 2 is 1/6. But a 3 occurs with probably 1/3. Okay, so that got me up to, I have 2/3 left. And now, because a little bit more carefully, and then let's say I've got, yeah, let's say this one is 1/6 and 1/12 and 1, so 12th. Okay, so this is a die that's more likely to roll a 3. And then I have, so die 2, which is fair. So 1, 2, 3, 4, 5, 6. That's a 2 somehow. So it's 1/6, 1/6, 1/6, 1/6, 1/6. Okay. What is okay, and what I'm going to do, I'm going to roll die 1. So I'm going to roll so 1 die, and I'm going to call this so roll 1, and then I'm going to roll so the other. Okay, but I don't know, and this will be roll 2, but I don't know which die is which. Okay, I know one is a fair die and one is going to be biased, but I don't know which one I rolled first and which one I rolled second. So I will have the random variable if I look at the first roll, okay, and I roll a, and on the first roll I roll a, so 1, okay. What's the probability? So this is the event here. So R1 equals a 1. This is event A, and R2 equals a 1. So this is, right, so this is the event B. Are events A and B independent of each other? Yeah. So yeah, A and B, and yeah, you agree? Anyone disagree? Okay. So A and B are going to be independent of each other. If I roll, the first one is 1/6, the second one is always going to be, so probably 1/6. So probably they're both 1/6 is 1/36, right? Okay, but are the random variables independent of each other? Is if I know the first roll, right? So if I know, like, what would I need for the random variables R1 and R2 to be completely independent of each other? What property would I need? Right? Remember what was the independence property I needed? I wrote it here someplace, right? What was the key thing? Yeah. Yeah, I need all values are going to be independent, all possible roles here. Okay. Okay, so are these random variables independent? Can you come up with another event? It doesn't have to be a multiple things, it could be, but that is not independent. No? Okay. Yeah, I haven't written down the joint product. I could. It's going to be 36 entries. So I have to just think about what it would be. Or like I want to know, can I store it with just the marginals? Is the marginals enough to store that whole table? That would mean that if they're independent, that's true. So I'm going to think through, can I, like if I wrote it all down, then you could probably spot it, right? But can you pick out something without me writing out the whole table? Okay. Yeah, so let's say A prime is R1 equals to 3. Okay. So if R1 is equal to 3, well, am I more likely to have rolled die 1 or so die 2? I'm more, yeah, I think I'm more likely to have rolled die 1, right? The probability, given that the outcome was 3, which one is, well, I probably rolled die 1 because it had a 1/3 chance of getting a 3. Right, so I've learned something about which die I've thrown. So I'm more likely roll 2 is more likely to be from die 2. Okay, so then if I set, say, B prime, it can be, it should be, well, let's say if I roll 2 equals to 3 again, well, then if I'm more likely to have rolled die 2, that's probably going to be closer to 1/6, right? But the overall probability is greater than 1/6, because if I'm rolling die 1 the second time, then I'm going to have a higher probability, because that one's more likely to be a 3. So these are not independent. I can kind of reason about this and know I can't store them just as the margins. That 3 outcome is going to affect the probability, so B prime. So this is tricky. What if instead I use event B double prime, which is R2 is equal to, so 1. Are A prime and B double prime going to be independent of each other? Yep. Yeah, that's right. These two events, A prime and B double prime, are independent of each other. Okay, so I have to have pick two values. They're not independent if I pick a 3 and say a 5, because they both have to differ. Otherwise, so most of the pairs of events across the rows are going to be independent of each other, but only the ones where I have both things having a different probability are going to be not independent. But that means the random variables are not independent. Okay, yeah. Yeah. Oh, right. Okay. So let's think through how would you, if you wanted to calculate the probability of B prime, given that A prime was true, right? Like, what tools would you feel comfortable using to do this, right? And remember, there's this kind of multi-stage process. I picked a die to roll first, I rolled it. And then the other one was die second, I rolled that. So I could probably use, like, I could construct a probability tree, right? Where I pick a die at random, 50-50, one half. Then I rolled the die, I saw the outcome. That's the next step. And then the third step is I rolled the other die. Right? You could calculate all these probabilities using one like the probability tree. That would be a way to calculate everything. It'd be messy. I'm not going to go through that example. Okay, but if you don't trust that these are A prime and B prime are not independent, you could go and verify that by calculating the probabilities and then the joint probabilities of the marginals and multiply them together. But you can kind of look at this and hopefully kind of reason about it, that if you rolled a 3 on the first roll, it's more likely you rolled die 1, right? And that means the second roll is probably die 2. All right, so now if I want to roll a 3 again, I've reduced my overall probability, because then I'm only going to get a 1/6 chance. I was hoping to get a larger chance of a 3, right? And I would have if I rolled die 1. So because I learned about which die is more likely to have occurred, then that influences the outcome of the second roll. And when something like this happens, you don't have independence. Even though you can be fooled into just checking just one of the events, or maybe most of the events are going to be independent, but not all of them are. So I have to be kind of careful in this case. So great. Okay, good. So this was a good thing to work through. What should I do? All right. I did not start continuous random variable joint independence today. We'll save this for after break. That'll be fine. I'm not going to try and do like 3 minutes of that. I don't. Let's do another example of this, and then I'll do the quick review for the quiz. Okay. Okay, I'm gonna let X and Y be two fair dice rolls. Okay, so now these dice are fair. I'm not playing with the non-fair dice. Okay, so it's a new example. Okay, okay, and let's say that so the event A is going to be X is that X is in the set 1, 3, and so 4, and event B is equal to Y is in 1, so 2. Okay. Are A and B independent? So events, right? So A and B are events. They're subsets of the possible outcomes. X and Y are the random variables, right? And there are 2 dies, 2 rolls of fair die. Right? It could be the same die I rolled twice. The same die. Dice is plural, right? I keep messing this up. Dice is plural. Die is like the singular. Okay, so I could have been the same die I rolled twice, or there are 2 dice and I rolled one then the other, but they're both fair die. Okay. Are the events A and B independent? So how would you go about thinking about this, right? So What's your strategy without telling me the answer? Yeah, right. Okay, so one way of doing this is to try and like write down the probabilities of the two events, right? Right. And so for A, that happens 1/2 of the time. B is 1/3 of the time. And then, but then to verify, I need to calculate the joint probability. And I could probably do that. I could work that out. Yeah, yeah, okay. And then, so how would I use that? So I want, right? So I want to check if probability of A times probability of B is equal to probability of A intersection B, right? And you think, and probability A, this was 1/2. You can get that pretty easily. Probability B is 1/3. So how would I check probability A intersection B? Yeah, there's a little simpler way holistically to approach this. Yeah. Yeah, so I could kind of think of this as the intersection. Let's say I have A and, well, this was actually X and Y, and I have, let's see, A is 1, 3, and 4, and B is 1 and 2. And so I just look at the intersection of these. Right, and I say that's 6 things out of 36. Okay, right, so I can calculate this is 6 out of 36. This is equal to 1/6. And, oh, so these are equal, right? 1/2 times 1/3 equals 1/6. Okay, so that's one way of doing it. This is not the way I was hoping you would find. Okay, well, this is a lecture about the independence of random variables. This is the independence of events way of approaching this. What do we know about the independence of random variables? Where are the random variables here? Yeah. Yeah, X and Y are random variables. Are those variables going to be independent? Who thinks they're independent? Who thinks they're not independent? Okay, and who didn't raise their hand? And who still didn't raise their hand? Okay. Okay. X and Y are going to be independent, and we should just know this, right? They're 2 die, and they're both fair die, and we rolled one, and then we rolled the other. Right? They're identical events. They're identical random variables, and they're independent of each other. What happened on the first die did not affect what happened on the second die. They aren't different die, and I didn't choose one or the other. They're just kind of 2 independent rolls of a random dice. Okay, and we should kind of be able to gauge this just by thinking about this. Okay, yeah. But if we had the same unfair die and the first one was unfair, the second one was fair. Okay, but do I roll that one twice? Okay, are X and Y, are they independent? Yes, they're still independent. The first roll does not affect the second roll. Now, the probability is not fair, but it's a probability distribution. The outcome of the first one, if I rolled, let's say one happened half the time and the rest were 1/12 of the time, or 1/10 of the time, right? And so I rolled the first die and then I rolled the second. Did that affect the roll of the second die? I know the PDF. It does not affect it. So those two PDFs are independent. Okay, so if I know that the random variables X and Y are independent, what do I know about the events? Without any calculations, what do I know? Yeah, in the back? Yeah, they have to be independent, right? If the random variables X and Y are independent, any events made up of their outcomes are also independent. Okay, so if I can reason about the fair die, like no one's going to tell you in the real world, oh yeah, these are independent. You kind of need to think and model it. And two independent rolls that doesn't affect, first one doesn't affect the other one, means that they're not influencing each other, even if they're not fair. Okay, so those events are going to be independent of each other, which means I can calculate them by the product. Good. Okay, so the first die is not fair. The second one is fair. I know the order. Are those independent? They're still independent. They're not identical anymore, but they're independent. And so I can still calculate the marginals and take the product to get the joint probability. Okay, last question, then we'll do a review for 10. That's correct. Yeah, they were not independent because we did not know the order. And that's why, knowing the outcome of the first roll, we can guess which die we rolled. We didn't know the order, but we can make a guess on it. And that guess affected the outcome for A prime and B prime. Not for A prime and B double prime, but it did for A prime and B prime. All right, okay, cool. So independence is something you kind of reason about and then you use to decompose it to the marginals. That's the most common way it comes up. It also helps with kind of the conditional probabilities. You can get rid of a conditional and a conditional probability as well, because if you know the events are independent. Okay, I want to do for 10 minutes, let me do a review for joint, discrete, so random variables. Okay, and I think this lecture was actually a pretty good review already. But let me say, what you want to think about is having a joint, so PDF, and that would be F, and I'm going to have two random variables, and we're going to call these M and C in some example I'm going to work out. Okay, and I'm going to get two of these random variables, and I'm going to get a joint PDF. So I write them both as a comma, and they're going to take on values. And in this example, we're going to say, we're going to have one is representing a college someone goes to, and we'll say Utah, or so BYU. And think of, we're not doing expectations, so don't worry about them not being real values, but you can assign them 0 or 1 or something like that if you want to. And then they're also the major in the college. And let's say you could major in computer science, in data science, or in statistics. Okay, and so what's the probability you major in statistics at the U? 0. You don't have a statistics major, right? You can do like some emphasis in the math department. What's probably you do data science major at so BYU? I don't think they have one of those. They have some other computational math sort of thing. Okay, and so let's say 0.2, 0.1, 0.5, and 0.2. Okay, so this joint PDF is represented as a table. Okay, well, think of this for discrete random variables. It's essentially a table. You could think about it in other ways, but it always exists as a table. Some entries could be 0. If I sum over all values, you know, I and j for f of MC, and I take on values I and bj, this is always equal to 1, right? So if I add up all of these values, they have to equal to 1. Okay, so that's, but now it's, yeah, I should write this as a double sum, right, over I and j. Right, so I have to sum over rows and columns, right? And if I add all those blue values up, it should equal to 1. Okay. The other thing is I can calculate the marginal probabilities of this. I can create the PDF of the college distribution of U or Y, right? And this is the sum. This is 0.1 plus 0.5, so 0.6. So the probability a student goes to Utah is 0.6, and the probability to BYU, so this is f of c of u, and f of c of y, this is equal to 0.4. Okay, these are the marginal, so probabilities. Marginal probabilities. Okay, and I can do the same thing for the rows. F of m of stats equals 0.2. F of m of data science, 0.1. And adding up here, F of m of CS equals 0.7. Right? And so those should also, I add the purple ones all up, those should also, those are going to also add up to 1. Okay? Yeah. Yeah, okay. So for expected value, I would need to assign some numerical values to these. Yeah, so we haven't, yeah, I haven't done, in this class, we're not going to do, I don't think we're going to do expected values over, yeah, so if I were to do expected values, I would need to assign values to these, like 0, 1 and 2, 0 and 1, something like that. And then I could, and then the expected value of, so I would really do, we'll kind of talk about this after break, but you would say, you would put a function on M and C. It might be M times C, it might be M plus C. And you can take the expected value of that, so random variable, right? So I have another random variable X, which is a function of M and C. And I can take the expected value of X. Okay. All right, so it could be M plus C, right? And take the expected value of that. And then I have probabilities over all the values of M and C, and I write out the value of X times the probability of all the M and C that those could take. You can think about expected values in like an element-wise way. So if I have high-dimensional vectors, I can, then you do element-wise expected value. That turns out to be the right thing to do. But yeah. Okay. Okay, so these are kind of Okay, the one last thing you might want to be able to do is to do the conditional. So the conditional probability, right? And that might be written as f of u given y equals f of m given that college equals u, right? So this would be the conditional. This gives me a conditional PDF of the major, given that the college is the University of Utah, right? And so this is equal to, again, f of MC for some value A. This is not going to be legible, but okay. So let me, and so, so this is calculated for this takes on a single value A for the major, right? So this is now not a joint probability. This is now just a regular PDF because so I'm doing the intersection of those, but condition on the college. So what I want to do is I get the so if I evaluate this at f of m given c equals u at so data science, I look at the probability that m equals data science, intersection college equals the u, divided by the probability of the college equals u, right? So this is the same way I calculate the conditional probability before, but now I can get like the PDF. I could write down the whole PDF in this way. On the quiz, we're not going to have you write down the whole PDF, but we may ask you to like evaluate something like this. Okay, so just this table way of thinking about the joint probability and then calculating the joint probability, the marginal probability, and the conditional probabilities in the table, which you kind of did earlier, but we're kind of phrasing it as the joint thing, and then you could check whether these things are going to be independent. Okay, so that's what you should kind of know how to do at the end of this week. All right, so everyone enjoy spring break, and we'll go to continuous joint random variables after break.